Today we're going to be looking at inverse functions. So we need to start talking about the difference between a relation and a function. A relation just expresses a relationship between two variables, and it can be an equation and set of ordered pairs or through a graph. The inverse of a relation is produced by interchanging the x values and the y values, or the input and the output. A relation and its inverse don't necessarily have to be functions. Recall that a function has only one output or y value for each input or x value and must pass the vertical line test. So let's take a look at example 1. Here is a relation in the form of ordered pairs. And if we take a look at each of these x values, there's only one y value that corresponds to each x value. For instance, for x value -2, there's only a y value of 2. For x value -1, there's only a y value of 1. For x value 0, there's only a y value of 0, etc. So the relation is a function. Now, if we want to write its inverse is produced by just taking each of those ordered pairs and interchanging their x and their y values. What you'll notice about the inverse, however, is that x value 2 now has two outputs. Or two y values. So the inverse is not a function. In B, our relation is in the form of an equation, x equals y squared. So if you look at an example, for instance, if x equals 9, y could be 3, but y could also be -3. So that means that an x value 9 has two different outputs, 3 and -3. So the relation is not a function. Its inverse is produced by interchanging the x and the y values. So the inverse is y equals x squared. And for it, for any x value, there is only one y value. The way I know this is, in order to get a y value, all you have to do is square an x value, and there's only one number that corresponds to the square of any x value. All right, so that is a function. So the inverse is a function. All right, in C, let's take a look at a relation that's represented as a graph. In this relation, we have several x and y pairs. So we can think of several of them, particularly the ones that fall on integer coordinates. And I can find 3 of those fairly easily. Let's take a look at the one at the top. It has an x value of 6 and a y value of 5. So if I'm going to graph the inverse of this relation, I'm going to graph the ordered pair 5, 6, interchanging the x value and the y value. There's also another ordered pair on the original relation, and that is the ordered pair 2, 1. So on the inverse, I'll graph the point 1, 2. On the original relation, there's also a point 2, -3. So on the inverse, I'll graph the point -3, that would be -2, correct? -3, -2. Now all we have to do is uh, connect these points to form the graph of the inverse. You'll notice that the edges of the inverse are very steep. So the opposite is going to be true when we graph the inverse relation. Now you'll notice the shape of these kind of resemble a cubic function and a cube root function, which are inverses or opposite operations of one another. Every function has an inverse, but the inverse may not necessarily be a function. In order for the inverse to be a function, the original function must be 1-to-1. A 1-to-1 function has only one x value for each y value. And so the graph of a 1-to-1 function must pass what's called the horizontal line test. So if I take a look at each one of these graphs in example 3, in example 2, if I pass a horizontal line through that parabola, we'll see that it intersects in 2 places. And if it intersects in more than one place, it fails the horizontal line test. And so this function is not 1-to-1. What you'll notice about the linear function in B is that no matter where I place a horizontal line, it will intersect with the line at most in one point. So this function is 1-to-1. And in C, this looks like a sine wave. We get multiple intersections for a horizontal line, so this is not 1-to-1. Notationally, an inverse of a function is written in the following way. This is read as f inverse of x. Notice that that -1 in the notation denotes an inverse and not an exponent. So to find the inverse of a 1-to-1 function, what we are going to do is, to make things easier, we'll replace f of x or whatever function we see with a y variable. Then we're going to interchange the x and the y, solve the equation for y, and then replace that y with function notation again, but this time it will be with the inverse function. So for g of x, in example 3, g of x equals 1/3 x minus 2 is equivalent to writing y equals 1/3 x minus 2. Now we're going to create the inverse by interchanging the x and the y. So the inverse would be x equals 1/3 y minus 2. Finally, we'll solve this equation for y, and to do so, I'll go ahead and clear the fractions by multiplying through by 3, and then solving for y, and finally replacing that y with g inverse of x. So g inverse of x is 3x plus 6. Now let's take a look at the graph of g of x and g inverse of x in the same coordinate grid. G of x is a line with a y-intercept of -2 and a slope of 1/3. So that green line represents g of x, and g inverse of x is a line with a y-intercept of 6 and a slope of positive 3. You may notice a lot of things about these graphs. Notice that the y-intercept of g inverse of x is the same as the x-intercept of g of x. That's because we interchanged x and y. In example 3b, we have a function h of x that's a cube root function. So first thing that we'll do is we'll replace that h of x with a y just to make the algebra a little bit simpler. And then we're going to create the inverse by interchanging the x and the y. So x is equal to 2 times the cube root of y plus 1 plus 3. And now we're going to solve this equation for y. So we have to think about the order of operations. If I were to plug a value in for y, the very first thing that I would do to evaluate is to add 1. Second thing would be cube root. Third thing would be times 2. And the last thing would be plus 3. So if we're trying to undo all of these operations to get y by itself, we'll have to do them in reverse order. So the first thing that to be done to solve for y is to subtract 3. The second thing is to divide by 2. The third thing is to undo the cube root. We can undo that cube root by cubing. So that will give us x minus 3 over 2 cubed is equal to y plus 1. And then the last thing would be to solve that for y by subtracting 1. So this is y equals x minus 3 over 2 cubed minus 1. Lastly, we'll replace that y with the notation h inverse of x. In the interest of time today, we're not going to graph this one in the same coordinate plane. In example 4, we need to find the domain, the x-intercept, and the y-intercept of function f of x. So let's go ahead and do those things. The domain of f of x is, since we have a division, the denominator cannot be 0, and if x plus 1 cannot be 0, that means that x cannot be negative 1. And in order to find an x-intercept, we let y equal 0. And then solve for x. So if we let y equal 0, 0 equals 2x minus 6 over x plus 1. And we know that a fraction is equal to 0 when its numerator is equal to 0. So that means that 0 is equal to 2x minus 6, the numerator of the fraction. And that gives us 6 is equal to 2x, and x is equal to 3. So our x-intercept is the point 3, 0. And then for our y-intercept, we let x equal 0 and solve for y. So let x equal 0. And our y value is 2 times 0 minus 6 over 0 plus 1. And that's going to give us a y value of negative 6. So that means that our y-intercept is the point 0, negative 6. All right, the next thing that we're going to do is to find the inverse of this function. So to find the inverse of this function, first we'll replace f of x with y. And then we'll create the inverse by replacing the y's with x's and the x's with y's. The next thing that we'll do is to solve for y. Now this can be a little bit tricky, so we'll have to use some clever algebra here. First thing that we need to do is to clear the fraction, or just multiply through by the denominator. So multiplying through by the denominator, we get x times y plus 1 is equal to 2y minus 6. Distributing, that's xy plus x is equal to 2y minus 6. Now, if our task is going to be to solve for y, we want to get all of the y terms on one side and all of the terms that don't have y on the other. So if we add 6 to both sides, we can get the x and the 6 on the same side. Those terms do not have y's in them. And then subtracting the xy from both sides, we can get all the terms that do have y in them on the other side. Lastly, factor out the y from the right side expression. And solve for y. Y is equal to x plus 6 over 2 minus x. And in inverse function notation, that would be f inverse of x is equal to x plus 6 over 2 minus x. So for the inverse, domain of the inverse is the denominator cannot be equal to 0, and you'll notice that the denominator would be 0 if x were 2, so x is not allowed to be 2. The x-intercept for the inverse function can be found by letting the y value equal 0. So that would be found by letting 0 equal x plus 6 over 2 minus x. And you'll remember that a fraction is equal to 0 when its numerator is equal to 0. So that would be when x plus 6 is equal to 0 or x is equal to negative 6. So our x-intercept is the point negative 6 comma 0. And now we'll find our y-intercept. To find the y-intercept, we let x equal 0. So that will be y equals 0 plus 6 over 2 minus 0. And that's going to give us a y value of 3. So that means that our y-intercept is the point 0, comma 3. Now you'll notice that our x-intercepts and our y-intercepts are switched. That is, if the x-intercept in the function was 3, then the y-intercept in the inverse was 3. And the same is true about the x-intercepts. We have a conjecture about the ranges of these functions. Think about the ranges as their y values. What happened when we created an inverse? We interchanged the x's and the y's. So essentially, we interchanged the domains and ranges. So that would imply that the range of f of x would correspond to the domain of f inverse. So the range of f of x should be y is not allowed to equal 2. The range of f inverse should correspond to the domain of f. The domain of f is x is not equal to negative 1. So that means that the range of f inverse is y is not equal to negative 1. All right, and the box at the top of the next page formalizes that relationship. The interval corresponding to the domain of a function is the same as the interval corresponding to the range of its inverse. It may be necessary to consider this if an algebraic representation for an inverse is not one-to-one, and we'll see an example of that in example number 5. Find the inverse of the square root function p of x equals the square root of x minus 3 plus 1, and then restrict the domain if necessary. So let's find the inverse of p of x. First thing we'll do is represent p of x using just y's and x's. And then we'll create the inverse by swapping the x and the y values. And again, if we think about order of operations, if I were to plug in a value for y, I would subtract 3, take its square root, and then add 1. So if I'm undoing those operations, we'll have to start by undoing the add 1, then undoing the square root, and then finally adding 3. So our inverse function is p inverse of x is equal to x minus 1 squared plus 3. Let's graph the square root function. And what we'll notice about the square root function is that its new origin is the point 3 comma 1. So I'm going to go over to 3 comma 1. That would be our 0, 0. And the next point on a square root function would be 1 comma 1, and then 4 comma 2. So we'd have a function that looks like that. Remember, the square root function is half of a parabola. So that would be the graph of p of x. Now, if we graph the graph of p inverse of x, that'll be our parent function y equals x squared. And its new origin would be at 1 comma 3. So if we'll go up to 1 comma 3, and then from there graph our parent function points for a parabola, what you'll notice about this one is that if I were to connect all 5 of those dots, we would see that the inverse is not actually a one-to-one function, and its shape is not exactly the same as the function p of x. Function p of x is only half of a parabola, so its inverse should only be a half of a parabola as well. Which half of the parabola will be determined by domain and range. So what we'll notice is that the range of p of x is the interval starting at y equals 1 up to infinity. So that means that the domain of p inverse of x should be the interval from 1 to infinity. So I'm going to put another little note on our inverse p of x and say that for p of x, we should just be looking at values of x that are greater than or equal to 1. And if we do that on the function to the right, you'll notice that now its graph matches up very nicely with the original function. So I'm going to get rid of those other 2 points that don't belong in the domain of the p inverse function. In example 2, we have the sine inverse function that we are so familiar with. And we're going to find the inverse of it. But before we even start, I'm going to recall that the output for sine inverse is negative pi over 2 to pi over 2. That is to say that the output is an angle on that interval. So when we're finding the inverse function, first thing I'll do is I'll let y equals sine inverse of x over 2, and then we'll interchange the x and the y. And then if I want to solve this for y, I have to think about order of operations. If I'm plugging in a y value, I would divide it by 2 first, then take the sine inverse. So the first thing to be undone is the sine inverse. We can undo that by using the sine function. So sine of x is equal to y over 2, and then y is equal to 2 sine x. So our inverse function is m inverse of x is equal to 2 sine x, and since the output for the sine inverse function is negative pi over 2 to pi over 2, then that means the input for the inverse function, or the domain of the inverse function, is also negative pi over 2 to pi over 2. In example 7, we're going to find the inverse of a rational function. So let's rewrite our rational function as y equals x over x minus 2, and then interchange the x and the y, and then try to solve for y. So I'm going to clear the fraction by multiplying through by the denominator, and then I'm going to try to get all of my y terms on one side by subtracting that y on the right, and all of the terms that don't have y on the other side by adding 2x to both sides. Factor out the y, and then divide, and we get y is equal to 2x over x minus 1. So that means that f inverse of x is equal to 2x over x minus 1. Now we're going to find the two compositions, f of f inverse. So f of f inverse is f of 2x over x minus 1, and that equals 2x over x minus 1 over 2x over x minus 1 minus 2. Remember that we can simplify the complex fraction by multiplying the top and bottom of the fraction by x minus 1. So that'll give us in the numerator 2x, and in the denominator 2x minus 2 times x minus 1, which is 2x over 2x minus 2x plus 2, or 2x over 2, or x. In the interest of time, we're not going to do the second composition, but note that that composition would also give us an output of x. So to show that two functions are inverses, it's important that we show that f inverse of f is x, and also f inverse of f is x. Note that showing two functions are inverse is not the same as actually finding the inverse. So if it says show that two functions are inverse, we must find their compositions and show that they are equal to x. That's it.